So, good morning. Welcome to the classroom. We continue with our discussion on the Liapunov's direct method for discussing the stability of autonomous systems. So, we look at this following system. Now we have P and Q with continuous partial derivatives in some neighborhood of 0, 0, and we assume Pxy equal to 0, Qxy equal to 0 for xy, or I'll just write P00 equal to 0, Q00 equal to 0. Okay. This is without loss of generalities. 0, 0 is assumed to be a critical point of the system. That is 0, 0 is here we are not assuming that P and Q are linear. Okay. So let us assume that we have P, Q continuously differentiable x and y D contained in R. D is of course open, and we have 0, 0 this is that. That's the status of the autonomous system that we are trying to look at. Okay. Now what we assume, so we have C defined by T naught, where xt naught equal to x naught, yt naught equal to y naught, and x naught, y naught. In other words, we are looking at the characteristic that passes through the point x naught, y naught. Okay, so this is the scenario that you have. This is some D and this is 0, 0. So x naught, y naught is some point here, and we are looking at a characteristic that passes through that. Say something like this. And this is at the time t equal to t naught. So an arbitrary point is xt. I mean, you can have some characteristic. I mean, this I am not particularly doing this, and this xt by t. So we are taking we have already seen that if you have some bounded region R in this, now you see that xt by t is defined for all t, and xt by t belongs to R. So if this is some bounded region R, that's what we have seen earlier. Now our interest is, this is an arbitrary characteristic. We want to know how the characteristics behave or what you call the flow lines behave, or what you call the trajectories behave in the neighborhood of the critical point which is also the equilibrium point zero. Now this is the question. Okay. Now in this regard, Liapunov's direct method is very handy. Okay, that is, we'll construct what is called the energy function, or you can call this energy function EXY. So we have defined the Liapumov function EXY defined on D such that EXY as a function E00 is 0 and is positive. That is, we have EXY is positive zero. That's what we mean by a positive definite function. Now we also assume further E is assumed to have the property that dE by is negative semi-definite. On D. These are the properties of the Liapumov function. A Liapumov function is one which is positive definite on D, that is, it is strictly positive. Okay, we also assume this is a continuous differentiable function. Okay. Continuous partial derivatives. So what we have is that E is a continuous function defined on D, having continuous partial derivatives with respect to x and y. It vanishes at 0, 0, and EXY is positive definite. That is, EXY is positive for every xy in D except at 0, 0. Further, it is assumed to have the following property, that dE by dx, Pxy, dE by dy, Qxy is negative semi-definite. So these are the attributes of the Liapumov function. That is, if you have a function having these properties, then you call that a Liapumov function. Okay? We don't know whether such functions exist, because you see that the crucial point is this, that is, there are several functions satisfying these properties. That is, it is positive definite, it is continuously differentiable, and it vanishes at 0, 0. There are several functions that you can define with that, but P is something that is given, Q is something that is given. So the crucial condition that we want E to satisfy is this: dE by dx P plus dE by dy Q is negative semi-definite on D. Okay? If such a function exists, then you call this the Liapumov function for the problem. So we call this, what is that? This one as 2. So this is the Liapumov function. Okay. Now what we have stated is this. We have stated the main theorem. If then It's a stable equilibrium point or critical point. Further, if is negative definite, that means it satisfies a stronger condition. This is negative semi-definite, which means that is strictly less than 0 0 0 where it vanishes, because we defined what is positive definiteness, semi-positive definite, semi-negative definite, negative definite, all these things. Then what we have is that it is asymptotically stable. At 0 0, where of course we assume it vanishes. And asymptotically stable equilibrium of okay, we have two parts for this result. One is just talking about stability, where the condition that we set is that this expression is negative semi-definite. Suppose we strengthen that condition to negative definite, then you get not only stability, the 0 0 is a stable equilibrium, not only 0 0 is a stable equilibrium point, but it's also asymptotically stable. Now there is a difference between what you mean by a stable equilibrium point and a asymptotically stable equilibrium point. The stable equilibrium point says that once a characteristic reaches some neighborhood of the equilibrium point, then it continues to stay in a neighborhood of the equilibrium point. Now this is the vague statement of that, which we have stated earlier more precisely. But in the case of a asymptotically stable equilibrium point, you see that every characteristic that is in a neighborhood of the equilibrium point will approach the equilibrium point. Now this is the difference between them. Okay, so we will prove this theorem. Okay, right. So what is the nature of the what you call the EXY? EXY, see, take this as the z-axis, this is the x-axis, this is the x-axis. Suppose this is the x-axis, this is the y-axis, this is the z-axis. Now EXY defines a surface in the XYZ plane of the type z is equal to EXY. So space defined on zero. It has a well-defined normal. Okay, and then it passes through E this is what you have. Okay, so it has a property of this kind, namely, so we can take functions of this type. Something like a paraboloid. So EXY or more generally as a surface and we are assuming, of course, sufficient smoothness, and xy zero, that is a tangent plane. Touches 0, 0. Okay, now let us start proving this. So this is the nature of the surface. Okay, now let us start working on the proof of the theorem. Okay. So let C1 be a circle of radius r, that is r square, contained in D, so that EXY is defined everywhere on C1. So E is defined everywhere on C1. So E is defined on C1, and you know that C1 is a closed bounded subset of R2. So C1 is a closed bounded subset of R2, that is, it is compact, and E is continuous. Therefore, E attains a minimum on this, and this minimum is going to be certainly positive. Okay, because C1 is compact and E is greater than 0 on C. By definition, E is continuous, so that hence it attains a positive maximum, a positive minimum So let me draw the picture of the xy plane. You have a circle here of radius, this is C1 r. So E attains a minimum value on C1, which you call, so maybe it attains at one point or several points or the whole entire C1 or whatever it is. So we can assume that this is a point where it attains the minimum value. Okay. Now, what you have is this. Therefore, inside C1 you can find another circle. So, not inside the okay. Now I'll write this. There exists a R positive, R strictly less than capital R, and a circle C2 with center at 0, that is C2 is defined as which is less than R. Such that what we can say is that EXY strictly less than M for XY disk enclosed by C2. So you have and here EXY less than small I. Okay, so let be a characteristic inside the circle C2 at that is xt naught yt naught is a point lying in the disk enclosed by or disk defined by the circle C2. Okay, so xt naught yt naught is some point here. Now you know that. So now we look at the behavior of this disk, or sorry, behavior of this characteristic. Okay. Okay. then what you have is this. See, what is dE by dt? See, we have earlier defined this. We defined Et as or I'll write it this way, P it is a function of t. Sorry, I'm sorry about that. So exy, et you define as yeah. Then what you have is this. See, dE by dt and on C, what you have dx by dt equal to P therefore what we have is this dE by dt all this dE by dx and dE by dy evaluated at xt by t. This is it. And this we have assumed that since is negative semi-definite, what we have is this dE by dt less than or equal to 0. Now this is the crucial thing. So this means is monotonically decreasing on C. That is on the characteristic C. Okay. So this is what you have. So what do you have? You have Et is less than or equal to Et naught, which is less than m. For every t, what does this mean? This means that Et is strictly less than m for all points on this characteristic. Okay, that means see the characteristic C cannot the region enclosed the region enclosed by C2. It is more or less trapped here. That is what we infer. Cannot reach the circle C1. So the minimum value attained on that C1 is m, and this is Et is strictly less than m, so it can never reach the circle C1. So it remains in the inside the circle C1. So once the characteristic C is in the region enclosed by it will never so that means once a characteristic is inside R, okay, it can never leave this region enclosed by C1. So what does it mean? So C remains zero. Okay, therefore, and this is true for every characteristic. Okay, for every characteristic you can get this, which implies all characteristics eventually it stays in the neighborhood of 0, 0. That is which implies stability of So let me draw the picture. So what happens is this. This is the xy plane. Now we have these circles that I have drawn here. This is C1. This is C2. Okay, and this is the particular surface E. Okay, now what happens is that, you see, you project these circles onto the surface. Okay, so that gives the, see, corresponding to any point here, the E value is given by what is called Z is equal to E of xy. Okay, and what happens to this E value, that is the height of the surface at the point xy to this. So this is, so once you are on a curve, then you see you get ET. ET keeps changing as you move along along the path C. You see that this E gets changing from point to point. But what we want to say is that because of these conditions, now you see the path is constrained to stay in the neighborhood of 0, 0, because ET can never be greater than small n. Okay, because of this condition. So that implies any characteristic once in the neighborhood of 0, 0 will remain in the neighborhood of 0, 0. And that means stability of the equilibrium point. So all characteristics have this property. Therefore, you see that 0, 0 is a stable equilibrium point. Yeah. Now we go on to prove the more constrained or more stringent situation. Is it asymptotically stable? So what is the basic assumption? The basic assumption is this, that so let us prove the case 2. Is if negative definite. This is the question that you are asking. Okay, the answer to this is yes. So let us prove this. To prove this, this is what you have. Suppose xt, yt be the characteristic C. Denoted by C. Okay. Then what do we have? We have that. So we want to prove that we want to prove that as infinity, as t tends to infinity. So it becomes asymptotically stable. So this is an arbitrary characteristic. A characteristic C. Okay. So if EXY is positive, and this what is that? Now we have seen that if it is negative definite, it is certainly negative semi-definite. Therefore, xy 0, 0 is a stable equilibrium. The question that you are asking is whether this is true or not. Okay. So we have, so d by dt q at is less than 0, negative. Of course, when xt by t not equal to 0, I mean x0, see, except at 0, 0. Okay. Therefore, Et monotonically decreasing. So Et is now a monotonically decreasing function. Now what we have is, you know that Et is certainly greater than or equal to 0. Et is monotonically decreasing, and somewhere in the circle, in the circle C, we have the function Et less than or equal to m. So you see that inside C1. That is, inside C1 means in the region enclosed by C1. Okay. Therefore, and it is monotonically decreasing. Therefore, it is clear that, so what you have is this, that is Et is a monotonically decreasing function bounded below by 0, which implies Et converges to a limit, well-defined limit L infinity. That means limit which is certainly positive. Greater than or equal to 0. Now we want to show that equal to 0. Then our contention is proved. So how do we prove this? Okay, we get to a contradiction. Assume L is positive. If L is positive, then choose R bar less than R such that less than L. That is possible. So what you have is this. You have another disk or circle here, C R bar C3, okay, whose radius is given by R bar. Okay, so let inside it has nothing to do with the differential equation, because it has only to do with the E function. Once E function is defined, this, and L is given, then R3 is fixed. R3 is chosen or can be chosen. There exists such an R3. Okay. So what you have is this. So we have that C3 is essentially defined as okay. Now what do we have? We have C definite. Therefore, it has a negative maximum. It has a negative maximum, say minus k, say minus k, between the circles C3 and C1. Okay, right? You see that this cannot be 0 except at the point 0, 0, but it is negative, it's continuous. Therefore, you see, inside the disk it attains a negative maximum. E value. Okay, therefore in this ring, so let me just wipe this part, clear it up. C1, C3, the entire path of C for T greater than or equal to T0 is complete. Because it already somewhere, it starts somewhere here, and then you see that it goes to a limit, and the limit is assumed to be positive. So we have already enclosed a region where, you know, the value of E is the value of E is greater than this particular L. That is the reason. So in the region enclosed by C3, you see that the value of L is value of EXY is greater than L. Is less than L, is strictly less than L. Okay, so somewhere here it has to be. It just goes to a limit, and it's a monotonically decreasing, and therefore this is the scenario. So what does it mean? What is the consequence of that? So you take dE by dt. So integral, say T0 T d tau. This is equal to T0. Okay, so if you write this up, so ET is d tau, and we use the fact that dE by d tau is that is this one, okay, has a negative maximum in this particular part, say minus k. Therefore you have the inequality ET is less than or equal to plus or minus T0. So now what you have is this. Therefore what does it say? It says as t tends to infinity, that is plus infinity, But you know that ET is, since this is a contradiction. Hence, L is equal to 0. So what we have assumed is that if L is greater than or equal to 0, then there is a contradiction. Okay. Therefore, what we have, L is equal to 0, which implies so every characteristic, so we started with an arbitrary characteristic. So every characteristic, once it is in a neighborhood of 0, 0, it approaches 0, 0. That is, all characteristics approach 0, 0 as t tends to infinity. Therefore, this implies the equilibrium point is a asymptotically stable equilibrium point. It is nice, beautiful geometry. See, what you have is ET is this, the scenario is this, so once you are inside a neighborhood, what happens is, see, this is the height, suppose this is the point, then this height is what you call ET, and you have a characteristic passing through this. What happens to this characteristic? This is what you are asking. And under the specified conditions, you see that you can only move towards 0 or you can only remain in the neighborhood of 0. So if it is positive, if this expression is negative semi-definite, then you can remain only in a neighborhood of 0, 0. Further, if it is also negative definite, then it not only stays in a neighborhood of 0, 0, but it also approaches 0, 0. Therefore, this is asymptotically stable. This is a conclusion. So that completes the result. So you see that this height is at a point, you take the point on the bowl, and that point is denoted as a ET. And what happens to ET is that as you move along C, the ET starts decreasing. Okay. So it says that ET cannot increase initially, that is when you assume only negative semi-definiteness for this expression. But if in addition it is also negative definite, then what happens is ET not only decreases, that it forces the characteristic can only approach 0, 0. Once it stay away, see, once this start going away from here, what happens? ET will start increasing, but that is not possible under the conditions. Okay, once the characteristic start moving away from this 0, 0, you see that the value of E along the characteristic, namely ET, will start increasing, and that is not possible. Okay, right? That's what we prove. That's an art of proving it. Okay, so that completes the proof of the theorem. Now we can look at some example. It's quite easy to work out. These are very simple examples. Okay, let's take the first example. Now investigate some example. First example. The first example is this. Consider the equation of motion. It's a one-dimensional motion given by a particle of mass m. This is the equation. This we have considered earlier. We assume C is a constant representing the viscosity of the medium. See, what is happening is that if you have a particle moving in a viscous medium, when the viscosity is high, there is a natural resistance towards this. And that viscosity, a constant representing this phenomena, gives a force which, if you have a higher resistance when you have a higher velocity. Okay. So that is C times dx by dt is the particular force that comes. This is the velocity and this is C is the constant and which has certain dimension. Okay, so that this becomes a force. Now this is the rate of change of momentum that you have. So the dimension of the entire set of terms is the dimension of this set of these terms. So if you see, like in water, if you are moving, or in a sort of heavy liquid, if you are moving, and the heavy liquid has higher viscosity, so the motion is really damped by the viscosity. That is the term that is represented by this. And the other one, this term corresponds to what is called it's like the movement of a spring. The more you stretch, what happens is it will resist, and then you leave, it will just return to the original position. Okay, this we have discussed earlier. Okay, so k greater than 0, k is positive, is called the spring constant. That's what I said. You have a spring like this. On which a mass is there. Then what happens? If you just pull this down, then the moment you leave it, it will come back. Okay. So if you pull it and leave it, then it will start oscillating. Right? It compresses, then it releases. If it stretches, then it compresses, and so on. So that is a spring action that you have. Okay. So the equivalent system is that is simple. So the only critical point of the system is zero, zero. So these are all things that we have analyzed earlier. Now we want to see whether you have a Liapumov function to understand the stability of this. Okay. So how Liapumov functions are constructed? Because they have nothing to do with P and Q. I mean, they are eventually, when it, see, we start with a positive definite function. Okay. So a typical positive definite function is, see, Exy equal to A so it's a bowl type function. So Z is equal to Exy is a bowl of this kind. Okay. That you can easily see with the assumption that A is positive, B is positive. It's a positive definite function. So we are certainly looking for such things. In this specific problem, it is the energy. I mean, see, this is being worked with the what is called physical intuition. The physical intuition says that you have equilibrium if the energy, total energy of the system attains a local minimum. Okay. So physically, is an equilibrium point, stable equilibrium point, if the total energy of the system is local minimum at 0, 0. Okay, so in this case, let us write down so we are going by physics. Okay, so we write down the energy, the total energy, the kinetic energy of the system is half mv square, v square is y square. Okay, and the potential energy is integral which is equal to x square. Therefore, the total energy is kinetic energy plus potential energy. So what you have is half k so this is the total energy. Okay. Now we compute. So we take EXY K and M are certainly positive. So M certainly positive. Therefore, E is positive definitely. And E00 equal to 0. Okay. Now we compute this dE by this turns out to be what is, see, the P is given by Y. Okay, so this is Kx Kxy plus okay, so let us work it out. So what happens? This is equal to, you can show that this is equal to Cy square, and you know that this is certainly less than or equal to 0. So this is a typical Liapumov function. That's why it is called, initially it is called, we started calling it an energy function. Even that notation E being used for it comes from that. So in this case, there exists a Liapumov function. Is this positive, negative? That is this expression negative definite? Yes, it is negative definite. Oh, sorry, it is, sorry. It is negative semi-definite. Okay. And this hence a stable equilibrium. Okay, now we look at another example. But you can show that this is actually when C is positive. So we can show that when C is positive, show that this equilibrium is stable, is asymptotically stable. That we can do with our, because you see the equation that you are considering is a linear equation. So we have our standard mode of analysis, and we have already shown that this is all characteristics collapse to the equilibrium point, or in the even in the physical consideration it is true. See, it goes like this, then comes back, and because of the pull towards origin, it crosses this, it doesn't go that much distance to the other side to have a simple harmonic motion. So because of the damping effect, you see that it goes like this, comes back, comes back, comes back, comes back, comes back, and this is if C is positive. That I have said earlier. Okay, but we cannot read it out, but this is not following above consideration. Because what we have is this is only negative semi-definite. Since it is negative semi-definite, we cannot say, you cannot apply the theorem to conclude that it is asymptotically stable, whereas you can independently prove that it is asymptotically stable. That is what we can do. Now we look at another example. Consider this equation. Square minus y cube. That's the system that is given. Now clearly 0, 0 is an isolated critical point. It's an isolated critical point. Now we choose EXY. So we have 4 parameters: A positive, B positive, M positive integers. Okay. Then you see that this is greater than or equal to 0 and E00 0. Now we have 4 parameters to play around with. Okay, so we will calculate this. This is equal to, you can work this out. This is in this case 2m a x to the power 2m minus 1 y plus 2n b y to the power 2n minus 1 cube. Okay. Now we simplify this. When we simplify this, this is what you get. Take this way, 4m a x to the power 2m y plus 2n b x square y to the power minus 1. I club that together, and this term I write as 2n b 2n plus 2. Okay, that comes from this term, y cubed term with a minus sign. Okay, so you see that this is anyway even power, therefore this term is positive, therefore this term is certainly negative. So this will, if you are able to choose a, b, m and n such that this term becomes 0, so that's a, so choose such that this is equal to 0. So if you do that, then you get essentially a equal to 1 that's simple to work out. So let me write that. So choose minus 4m a see this is 0. See this automatically selects, you see 2m equal to 2, therefore m is equal to 1, and y to the power 1, so 2n minus 1 should be equal to 2, so that implies m equal to 1 and n equal to 1. Okay, so that is an automatic choice. Now you have to choose for this, with this you have to choose a and b. Now choose a equal to 1, b equal to 2. Okay, then if you make this choice, then you see that exy is equal to this is equal to minus which is strictly so this is strictly negative, therefore what you get, so 0 0 is once again we cannot conclude that it is asymptotically stable for this. Okay, so now so the art of choosing such a function is this. Okay, so we will and then manipulate with these various parameters that you have. Okay, so if you have more parameters that can be brought in, then it will be easier to fix the numbers. So that's the art. So let me now just give a theorem which is the following. Which is useful in fixing such functions. So exy ax square plus cy square, a quadratic expression. This is positive definite if and only if a positive and b square minus 4ac is negative. That is easy to prove, and it is negative definite if and only if a is negative and b square minus negative. That's a general theorem to fix such functions. See, quite often these kind of functions will help you with the choice of a, b, c. You will get the appropriate e identified. So this is a general theorem on this particular type of function about its positive definiteness. And if you can reduce the d by dx p plus d by dy q to one of this a term of this kind, then there also we have negative definiteness under these conditions. Okay, so let us prove this proof. It's very simple. If y is equal to 0, ax squared, and exy is positive definite not equal to 0 if and only if a is positive. So that fixes the case for y equal to 0. So if y is not equal to 0, then you can write exy as a into so this is already non-negative. Okay, so is positive definite if and only if is positive so this is anyway positive for large That is because higher powers of x by y comes there. Okay. Now this is positive for all x by y if and only if b square minus negative. Of course, a positive. I am taking a positive. And this is negative. Okay. So this proves the first part. Now, to prove the second part, use the fact that E is positive definite or right, E is negative definite minus E is positive. So we already know what do we mean by minus E is positive definite. Apply that so you get the result. Okay, thank you very much. That completes the proof.